This is a simple regression video on data visualization. In simple linear regression, we fit a straight line to the entire data set. In simple analysis of covariance, we fit one straight line per group. As an example of a simple linear regression, we might use pre-rehabilitation functional status as the predictor x, and post-rehabilitation functional status as the outcome y. As an example of a simple analysis of covariance comparing two types of rehabilitation facility, we'd also fit similar regression lines. The only difference is that we'd fit one line per facility. Accordingly, the visualization exercise is the same for both types of design. Namely, we ask whether the data in question fit a straight line. To assess whether the data fit a straight line, we recommend you approach the question both theoretically and empirically. The theoretical component of the assessment applies to a conceptual model of how the predictor and outcome are related. The empirical component of the assessment involves actually looking to see how well the fit works. If the empirical assessment is uncertain, the theoretical component might be used to break the tie. For example, one of the conceptual models used in rehabilitation after a stroke assumes that its impact is directly proportional to initial functional status, thus that patients with poor initial functional status will have greater absolute gains than patients whose initial status is good. Such a relationship would be well represented by a straight line. As an example of a conceptual model that suggests something other than a straight line, suppose you believe that a routine physical examination has an ideal duration. Too short and the encounter is rushed, or it's too long and the patient begins to chafe at the perceived inefficiency. Accordingly, a regression with exam duration as the predictor and satisfaction with the encounter as the outcome would be expected to appear quadratic rather than linear in form, which would suggest using a model of two predictors, duration and duration squared. For the present purposes, that is for models with a single predictor, the empirical assessment is quite straightforward. For models with multiple predictors, the visualization step can become much more complicated. We'll defer discussion of these issues until subsequent videos. For visualizing single predictor models, what you should do is create a scatter plot relating x and y, attach a fitted line, and check for problems that are so obvious they jump off the plot and scream for your attention. The most likely problems are listed in this slide. More subtle problems that don't jump off the scatter plot probably don't matter. In statistical lingo, regression is robust to modest departures from its assumptions. This includes modest departures from the assumption of normality, which is why we haven't made a big deal about it. Purely as a point of statistical culture, because this is an ideal to generalize, and so is something that you might encounter when you work with a statistician, a high-tech way to check for linearity is to fit a general-purpose smooth curve to the data. This general-purpose curve has a straight line as a special case. In other words, if the data are approximately linear, the smooth curve will look a lot like a line, whereas if the data aren't linear, the smooth curve will look quite different. Because the straight line is a special case of the more general curve, it can't fit better than the general curve and will probably fit worse. If the fits are similar, the interpretation is that a straight line is adequate. If the fits are very different, the interpretation is that a straight line isn't. This slide illustrates the low-tech approach of just looking at the scatter plot. Obviously, the linearity assumption is violated, and a quadratic model should be used instead. This slide illustrates what most typically goes wrong with the assumption of equal variances. As the value of the predictor increases, so does the level of variation. The distinction between leverage points and outliers is that leverage means an unusual value of the predictor, and outlier means an unusual value of the outcome. Suppose that this plot describes the data for a group of men who are all married to young women. I've drawn a positive relationship between x and y for these younger men. Now I've added the 95-year-old man. If I extrapolate the line for the younger men, it will lead to huge residual for the 95-year-old. Thus, this won't be the best fitting line. Instead, the best fitting line will have to fall very near the data value for the 95-year-old man, even though we've lost the relationship between x and y within the main body of data. In essence, it's as if this regression is only using two data points, one for the 95-year-old man and one representing a typical younger man. Although we'll use quantitative tools to check for outliers in multi-predictor models, for single predictor models, the simplest thing to do is just look at the scatter plot. If the data point doesn't immediately attract your attention, it probably isn't enough of an outlier to matter. As a final note, there's no need to check the distribution of y for normality. This assumption applies to the error terms, not to the values of y, nor is there a need to check the distribution of x for normality.